11th International Physics Olympiad, year 1979, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F. 1996. Problem number 1. A space rocket with mass m equal 12 tons is moving around the Moon along the circular orbit at the height of h equal 100 kilometers. The engine is activated for a short time to pass at the lunar landing orbit. The velocity of the ejected gases u equal 10⁴ meters per second. The Moon radius rm equal 1.7 multiplied by 10⁻³ kilometers. The acceleration of gravity near the Moon surface gm equal 1.7 meters per second square. First question. What amount of fuel should be spent so that when activating the braking engine at point A of the trajectory, the rocket would land on the Moon at point B, figure 1. Question 2. In the second scenario of landing at point A, the rocket is given an impulse directed toward the center of the Moon. To put the rocket to the orbit meeting the Moon surface at point C, figure 2. What amount of fuel is needed in this case? Solution for problem number 1. First question. During the rocket moving along the circular orbit, its centripetal acceleration is created by Moon gravity force. So it means that we have this first equation from which we can find v square. That will be after using expressions for acceleration on the Moon surface. We have v square equal g r square over r plus h. After calculations we can find that this speed on initial Moon orbit we have v equal 1652 meters per second. The rocket velocity will remain perpendicular to the radius vector OA after the braking engine sends tangential momentum to the rocket. See figure 1. The rocket should then move along the elliptical trajectory with the focus in the Moon's center. Denoting the rocket velocity at point A and the point B as VA and VB, we can write the equations for energy and momentum conservation as follows. Now we can use a second equation to express VB through VA and put it to the first equation, and we will get this one. So we can use it to find what is VA square. It will be this one. Taking expression for V in account, we can find velocity change at point A like this. Now we can find the velocity difference subtracting from V, VA, and we will get 24 meters per second. Since the engine switched on for a short time, the momentum conservation law in the system rocket fuel can be written in the form of m minus delta m multiplied by delta v equal delta m multiplied by u, where delta m is the burnt fuel mass. And now along that delta v much less than u, we will find that delta m equal approximately 29 kilogram. That was solution for question A. Solution for question 2. In the second case, the vector is directed perpendicular to initial vector. Thus we have these two expressions for the vector VA. Based on the energy conservation law in this case, and from the momentum conservation, the equations can be written in the form of these two equations. Also, we can use formula from previous question 1, that V square equal G multiplied by R square over R plus H. Solving these two equations, again using initially expression for Vc through V, we can rewrite them in form of this one, and using expression from V square, putting here, we finally get that delta V square equal G over R plus H multiplied by H square. And from here we can find what is delta V. That will be 97 meters per second. After that we can do the same manipulation. Using the momentum conservation law, we obtain that delta M now equal 115 kilogram. The only thing I have to emphasize that there are no guarantee that point of land will be in point C, means 90 degrees from initial position, because this lowest position for this ellipsis could be in any other point. So that was a solution for question number 2 and for the full problem number 1.